So now let's look at all these various families and groups on the table itself. Here is the groups separated out. You can see over on the left here you have the 1A alkaline metals, the 2A alkaline earth metals, and over on the right you have the 8A noble gases, the 7A halogens, the 6A oxygen group or calogens, 5A nitrogen group, the 4A carbon family, and the 3A boron family. Aluminum is in that group. You notice here green is the metalloids, yellow or kind of yellow looking is the nonmetals, and then everything else here is metals. Now across here is what we've called the transition elements or transition. Now if we fill this in with the various elements that fall into these places, you can see it's a little bit out of focus, but you can see the alkaline metals here, lithium, sodium, potassium, etc. The alkaline earth metals, beryllium, magnesium, calcium, etc. And then over here, you have the nonmetals in this group, and the metalloids in here. Now this is kind of an interesting way to draw the metalloids. I wouldn't recommend this. I think that the way the other tables do, like this, is much better. And then over here, the halogens, fluorine, chlorine, bromine, and iodine. The noble gases, helium, neon, argon, krypton, xenon, and so forth. And the relationship that these have to each other and so forth is very useful. And as we go along, you'll see it's very useful in the practice of chemistry. Now, a period is a horizontal row on the periodic table. Remember, the vertical column is called the group or family. A period is a horizontal row. Now, elements in one particular period do not have the same properties, obviously. Elements in a group or a column in the same group or the same column do have similar properties, but elements in the same period do not. The period number tells the number of energy levels of electrons that are present. What that means is that if you're in the first period, which is only hydrogen and helium, there's only one energy level, which means there's only one shell of electrons. The elements in period 2 have two shells or two energy levels for electrons. They have the first shell, which is also occupied by the more simple elements, and then the next shell, which makes up the new electrons that these new elements acquire. Left to right on a period decreases the metallic qualities and increases the non-metallic qualities. So as you travel from the left side of the table, for example, if you look on the table on the very left, you'll see the symbol Na, which stands for sodium. As you move across that horizontal row, the farther to the right you go, the less metallic a material is. And so that by the time you get to something like silicon or phosphorus, you have a very non-metallic material. And over on the other side of that, chlorine, Cl, is very much a non-metal. So here's an example. This looks at, here's the first period, is these two elements. Hydrogen, you see this one energy level with one electron in it. Helium, you see two electrons at that energy level. Then as you go to the second row, the second period, you have lithium has the these 2 electrons in the first energy level, but now a second energy level. So this is the second period. So there are 2 energy levels, and you can see every one of these has 2 little rings. And in the first little ring, they're all 2 electrons. But as you travel from left to right, you increase the number of electrons in the second ring, or the second energy level. Remember, a 4A has 4 valence electrons. 5A has 5 valence electrons, 5 little dots in the second ring. 6A has 6, 7A has 7, and 8 has 8. Then when you go to the third period, starting with sodium, you see that you start out with something that looks like neon, and then the third energy level has 1 electron. And again, this is in that first group, so it has 1 electron on the third period. And you go across and the pattern repeats. So it makes sense, if you look, that every one of these have the same number of electrons in their outer shell, 7, so their reactivity would be very similar to each other. What you can also see is that the size of the atoms get larger as you go down a particular group. And that's exactly what we show here. If you notice, at any group, which it means any horizontal or vertical column, as you go from the top to the bottom, the size, the atomic size increases. So as you go from the top to the bottom, the atomic size increases. Now, what is not necessarily as obvious, but is also true, as you go from left to right, the size also decreases. So the larger atoms are over here on the left, and as you go this way, you see that they get smaller and smaller. So as the energy level gets more and more full of electrons, it actually shrinks in size. And so the two trends I want you to know here is as you go from the top to the bottom, it gets larger. As you go from left to right, it gets smaller. So let's look at a couple of problems. And for each one of these, once we look at the pair, you look at your periodic table and formulate an answer, and then I'll tell you the answer. So which one of these, the sodium or the potassium, is larger? If you're looking on the left side of your periodic table, you can see sodium and potassium is right underneath it in the same column. Remember, I said as you go down the column, the atom gets larger. And so that means the larger atom is the potassium atom, which is the K. How about chlorine and bromine? Now you have to look on the right side of your periodic table. You see on the right there, the chlorine is above the bromine, or the bromine is below the chlorine, which means that the bromine is the larger atom. Now, sodium and chlorine, this is that other rule, which states as you go from left to right in the same period, same horizontal row, you get smaller. And so sodium's on the left, chlorine's on the right, so chlorine is going to be smaller, sodium is going to be the large atom. So you circle sodium. And sodium plus, now remember, sodium plus becomes sodium plus by losing an electron. And if you lose an electron on your outer shell, you're going to get smaller. And so sodium plus is actually smaller, and sodium is bigger, so you would mark sodium. There's another trend, which is the energy required to remove an electron. The energy required to remove an electron is called the ionization energy. Makes sense because you form an ion, so the energy required to move an electron and form an ion would be called the ionization energy. Now this table shows you the trend for ionization energy. And first of all, let's look at columns. What happens to the ionization energy in the columns? The rule is that as you go down the column, you decrease ionization energy. Or as it shows in the arrow here, As you go up the column, you have increased ionization energy. So that means that the ionization energy to pull an electron off of lithium, which is Li, is greater than the ionization to pull an electron off of sodium. And this makes total sense. The electron in lithium is in the second is in a second shell, which is closer to the positive nucleus holding it in, than the electron in the sodium, which is in the third shell, which is farther away. As you go from left to right, the ionization energy also increases, which also makes sense because the farther to the right you go, the more likely it is that you can fulfill the rule of octet. And so, for example, fluorine, which is over here on the right next to neon, fluorine, which is a symbol F, has 7 electrons, and all it needs is one more electron added. So trying to remove one is going to be extremely difficult. So we can do the same exercise, but this time we're going to pick the atom which has the higher ionization energy. So let's take our 2 right here, sodium and potassium. Sodium was above potassium, and we said potassium was the larger, but sodium in this case, as you go up the column, the ionization energy goes up. And so sodium has a higher first ionization energy than potassium. Let's do our bromine and chlorine. Both of these have very high ionization energies, but again, the rule is you go up, the ionization energy goes up. So the higher ionization energy would be chlorine compared to bromine. And sodium to chlorine, one is on the left side, one is on the right side. The one on the left is always less than the one on the right in the same period. And so the higher ionization energy would be chlorine. And this last one, the sodium ion has already lost its 1 electron. So now it has 8 electrons, so it's happy. So it's going to have an extremely high ionization energy, whereas the sodium atom is not. So the sodium ion is going to have a very high ionization energy. Now this is the last slide, and this slide basically reviews all 3 things that we talked about. Don't get into electron affinity. We didn't talk about electron affinity. We don't care about electron affinity right now. But we did talk about atomic radius or atomic size. We did talk about ionization energy, and we did talk about metallic versus non-metallic character. And what you can see is that this slide helps you review all 3 of those properties. Ionization energy increases from left to right and from bottom to top. Ionization energy increases from left to right and from bottom to top. Atomic radius increases from right to left and from top to bottom. So exactly the opposite of ionization energy. And then metallic character is actually exactly opposite to each. As you go more to the left and more to the bottom of the table, you have more metallic character. As you go more to the right and more to the top of the table, you get more non-metallic character. So this slide encompasses virtually everything you need to know about the periodic trends that we'll talk about in this course.